Hello, it's Vocal SENPAI. In this series, every chapter of the whole NCERT Chemistry book will be covered in audiobook format. Before going into the chapter, if you want handwritten notes of physics and chemistry, check out the links in the description. Now, sit back, relax and let's listen and learn. Classification of elements and periodicity in properties. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students, it suggests new avenues of research to professionals, and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of the chemistry, the chemical elements. Glenn T. Seaborg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows as a logical consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. 3.1 Why do we need to classify elements? We know by now that the elements are the basic units of all types of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man-made. Efforts to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. Not only that it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. 3.2 Genesis of periodic classification. Classification of elements into groups and development of periodic law and periodic table are the consequences of systematizing the knowledge gained by a number of scientists through their observations and experiments. The German chemist Johann Dobereiner in early 1800s was the first to consider the idea of trends among properties of elements. By 1829 he noted a similarity among the physical and chemical properties of several groups of three elements, triads. In each case, he noticed that the middle element of each of the triads had an atomic weight about halfway between the atomic weights of the other two, table 3.1. Also the properties of the middle element were in between those of the other two members. Since Dobereiner's relationship, referred to as the law of triads, seemed to work only for a few elements, it was dismissed as coincidence. The next reported attempt to classify elements was made by a French geologist, A.B. de Chancourtois in 1862. He arranged the then known elements in order of increasing atomic weights and made a cylindrical table of elements to display the periodic recurrence of properties. This also did not attract much attention. The English chemist John Alexander Newlands in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element, table 3.2. The relationship was just like every eighth note that resembles the first in octaves of music. Newlands's law of octaves seemed to be true only for elements up to calcium. Although his idea was not widely accepted at that time, he, for his work, was later awarded Davy Medal in 1887 by the Royal Society, London. The periodic law, as we know it today, owes its development to the Russian chemist Dmitry Mendeleev, 1834 to 1907, and the German chemist Lothar Meyer, 1830 to 1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties, such as atomic volume, melting point and boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newland's, Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Dobereiner initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows. The properties of the elements are a periodic function of their atomic weights. Mendeleev arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the same vertical column or group. Mendeleev's system of classifying elements was more elaborate than that of Lothar Meyer's. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. He realized that some of the elements did not fit in with his scheme of classification if the order of atomic weight was strictly followed. He ignored the order of atomic weights, thinking that the atomic measurements might be incorrect, and placed the elements with similar properties together. For example, iodine with lower atomic weight than that of tellurium, group 6, was placed in group 7 along with fluorine, chlorine, bromine because of similarities in properties, Fig. 3.1. At the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of the elements were still undiscovered and, therefore, left several gaps in the table. For example, both gallium and germanium were unknown at the time Mendeleev published his periodic table. He left the gap under aluminium and a gap under silicon, and called these elements eka-aluminium and eka-silicon. Mendeleev predicted not only the existence of gallium and germanium, but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements and those found experimentally are listed in Table 3.3. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table published in 1905 is shown in Fig. 3.1. 3.3 Modern periodic law and the present form of the periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound developments in theories about subatomic particles. In 1913, the English physicist Henry Moseley observed regularities in the characteristic X-ray spectra of the elements. A plot of root V, where is V frequency of X-rays emitted, against atomic number Z, gave a straight line and not the plot of root V versus atomic mass. He thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was, therefore, accordingly modified. This is known as the modern periodic law and can be stated as: the physical and chemical properties of the elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium, like actinium and protoactinium, are also found in pitch blende, an ore of uranium. It stimulated renewed interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived elements. You may recall that the atomic number is equal to the nuclear charge, i.e., number of protons or the number of electrons in a neutral atom. It is then easy to visualize the significance of quantum numbers and electronic configurations in periodicity of elements. In fact, it is now recognized that the periodic law is essentially the consequence of the periodic variation in electronic configurations, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reactions and valence, whereas others stress the electronic configuration of elements. A modern version, the so-called long form of the periodic table of the elements, Fig. 3.2, is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called periods, and the vertical columns, groups. Elements having similar outer electronic configurations in their atoms are arranged in vertical columns, referred to as groups or families. According to the recommendation of International Union of Pure and Applied Chemistry, UPAC, the groups are numbered from 1 to 18, replacing the older notation of groups IA, VIIA, 8, IB, WIB and 0. There are altogether 7 periods. The period number corresponds to the highest principal quantum number, n, of the elements in the period. The first period contains 2 elements. The subsequent periods consists of 8, 8, 18, 18 and 32 elements, respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum on the basis of quantum numbers of 32 elements. In this form of the periodic table, 14 elements of both 6th and 7th periods, lanthanoids and actinoids, respectively, are placed in separate panels at the bottom star. 3.4 Nomenclature of elements with atomic numbers 100. The naming of the new elements had been traditionally the privilege of the discoverer or discoverers, and the suggested name was ratified by the UPAC. In recent years, this has led to some controversy. The new elements with very high atomic numbers are so unstable that only minute quantities, sometimes only a few atoms of them, are obtained. Their synthesis and characterization, therefore, require highly sophisticated, costly equipment and laboratory. Such work is carried out with competitive spirit only in some laboratories in the world. Scientists, before collecting the reliable data on the new element, at times get tempted to claim for its discovery. For example, both American and Soviet scientists claimed credit for discovering element 104. The Americans named it Rutherfordium, whereas Soviets named it Kurchatovium. To avoid such problems, the UPAC has made recommendation that until a new element's discovery is proved and its name is officially recognized, a systematic nomenclature be derived directly from the atomic number of the element using the numerical roots for 0 and numbers 1 to 9. These are shown in Table 3.4. The roots are put together in order of digits, which make up the atomic number, and IUM is added at the end. The UPAC names for elements with Z above 100 are shown in Table 3.5. Thus, the new element first gets a temporary name, with symbol consisting of 3 letters. Later, permanent name and symbol are given by a vote of UPAC representatives from each country. The permanent name might reflect the country or state of the country in which the element was discovered, or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by UPAC. 3.5 Electronic configurations of elements and the periodic table. In the preceding unit, we have learnt that an electron in an atom is characterized by a set of 4 quantum numbers, and the principal quantum number, n, defines the main energy level known as shell. We have also studied about the filling of electrons into different subshells, also referred to as orbitals, s, p, d, f, in an atom. The distribution of electrons into orbitals of an atom is called its electronic configuration. An element's location in the periodic table reflects the quantum numbers of the last orbital filled. In this section, we will observe a direct connection between the electronic configurations of the elements and the long form of the periodic table. A. Electronic configurations in periods. The period indicates the value of n for the outermost or valence shell. In other words, successive period in the periodic table is associated with the filling of the next higher principal energy level, n is equal to 1, n is equal to 2, etc. It can be readily seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. The first period, n is equal to 1, starts with the filling of the lowest level, 1s, and therefore has 2 elements, hydrogen, Ls1, and helium, Ls2, when the first shell, K, is completed. The second period, N is equal to 2, starts with lithium and the third electron enters the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration 1s22s2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the L shell is completed at neon, 2s22p6. Thus there are 8 elements in the second period. The third period, N is equal to 3, begins at sodium and the added electron enters a 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. The fourth period, N is equal to 4, starts at potassium and the added electrons fill up the 4s orbital. Now you may note that before the 4p orbital is filled, filling up of 3d orbitals becomes energetically favorable and we come across the so-called 3d transition series of elements. This starts from scandium, Z is equal to 21, which has the electronic configuration 3d14s2. The 3d orbitals are filled at zinc, Z is equal to 30, with electronic configuration 3d104s2. The fourth period ends at krypton with the filling up of the 4p orbitals. Altogether we have 18 elements in this fourth period. The fifth period, N is equal to 5, beginning with rubidium, is similar to the fourth period and contains the 4d transition series starting at yttrium, Z is equal to 39. This period ends at xenon with the filling up of the 5p orbitals. The sixth period, N is equal to 6, contains 32 elements and successive electrons enter 6s4f5d and 6p orbitals, in the order, filling up of the 4f orbitals begins with cerium, Z is equal to 58, and ends at lutetium, Z is equal to 71, to give the 4f inner transition series which is called the lanthanoid series. The seventh period, N is equal to 7, is similar to the sixth period with the successive filling up of the 7s5f6d and 7p orbitals and includes most of the man-made radioactive elements. This period will end at the element with atomic number 118, which would belong to the noble gas family. Filling up of the 5f orbitals after actinium, Z is equal to 89, gives the 5f inner transition series known as the actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. B. Groupwise electronic configurations. Elements in the same vertical column or group have similar valence shell electronic configurations, the same number of electrons in the outer orbitals, and similar properties. For example, the group 1 elements, alkali metals, all have ns1 valence shell electronic configuration as shown below. Thus it can be seen that the properties of an element have periodic dependence upon its atomic number and not on relative atomic mass. 3.6 Electronic configurations, anti-YPES of ELEMENTS, S, E, D, F blocks. The Aufbau, build-up, principle and the electronic configuration of atoms provide a theoretical foundation for the periodic classification. The elements in a vertical column of the periodic table constitute a group or family and exhibit similar chemical behavior. This similarity arises because these elements have the same number and same distribution of electrons in their outermost orbitals. We can classify the elements into 4 blocks, viz. S block, P block, D block and F block depending on the type of atomic orbitals that are being filled with electrons. This is illustrated in Fig. 3.3. We notice 2 exceptions to this categorization. Strictly, helium belongs to the S block, but its positioning in the P block along with other group 18 elements is justified because it has a completely filled valence shell, 1s2, and as a result, exhibits properties characteristic of other noble gases. The other exception is hydrogen. It has only one s electron and hence can be placed in group 1, alkali metals. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to a group 17, halogen family, elements. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown in Fig. 3.2 and Fig. 3.3. We will briefly discuss the salient features of the 4 types of elements marked in the periodic table. More about these elements will be discussed later. During the description of their features, certain terminology has been used which has been classified in section 3.7. 3.6.1 The S-block elements. The elements of group 1, alkaline metals, and group 2, alkaline earth metals, which have ns1 and ns2 outermost electronic configuration belong to the S-block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electrons readily to form 1+ ion in the case of alkaline metals or 2+ ion in the case of alkaline earth metals. The metallic character and the reactivity increase as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S-block elements, with the exception of those of lithium and beryllium, are predominantly ionic. 3.6.2 The P-block elements. The P-block elements comprise those belonging to group 13 to 18, and these together with the S-block elements are called the representative elements or main group elements. The outermost electronic configuration varies from Ns to Np1 to Ns to Np6 in each period. At the end of each period is a noble gas element with a closed valence shell Ns to Np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electrons. The noble gases thus exhibit very low chemical reactivity. Preceding the noble gas family are 2 chemically important groups of nonmetals. They are the halogens, group 17, and the chalcogens, group 16. These 2 groups of elements have highly negative electron gain enthalpies and readily add 1 or 2 electrons respectively to attain the stable noble gas configuration. The nonmetallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. 3.6.3 The D-block elements, transition elements. These are the elements of group 3 to 12 in the center of the periodic table. These are characterized by the filling of inner d orbitals by electrons and are therefore referred to as D-block elements. These elements have the general outer electronic configuration N1, D1-10, NS0-2 except for PD where its electronic configuration is 4D10-5S0. They are all metals. They mostly form colored ions, exhibit variable valence, oxidation states, paramagnetism, and oftenly used as catalysts. However, Zn, Cd and Hg, which have the electronic configuration N1, D10, NS2, do not show most of the properties of transition elements. In a way, transition metals form a bridge between the chemically active metals of S-block elements and the less active elements of groups 13 and 14, and thus take their familiar name, transition elements. 3.6.4 The F-block elements, inner transition elements. The 2 rows of elements at the bottom of the periodic table, called the lanthanoids, Ce, Z is equal to 58, Lu, Z is equal to 71, and actinoids, Eth, Z is equal to 90, Lr, Z is equal to 103, are characterized by the outer electronic configuration N2, F1-14, N1, D0, 1, NS2. The last electron added to each element is filled in F orbital. These 2 series of elements are hence called the inner transition elements, F-block elements. They are all metals. Within each series, the properties of the elements are quite similar. The chemistry of the early actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states possible for these actinoid elements. Actinoid elements are radioactive. Many of the actinoid elements have been made only in nanogram quantities or even less by nuclear reactions, and their chemistry is not fully studied. The elements after uranium are called transuranium elements. 3.6.5 Metals, nonmetals and metalloids. In addition to displaying the classification of elements into S, P, D, and F blocks, Fig. 3.3 shows another broad classification of elements based on their properties. The elements can be divided into metals and nonmetals. Metals comprise more than 78% of all known elements and appear on the left side of the periodic table. Metals are usually solids at room temperature. Mercury is an exception. Gallium and cesium also have very low melting points, 303 K and 302 K respectively. Metals usually have high melting and boiling points. They are good conductors of heat and electricity. They are malleable, can be flattened into thin sheets by hammering, and ductile, can be drawn into wires. In contrast, nonmetals are located at the top right-hand side of the periodic table. In fact, in a horizontal row, the property of elements change from metallic on the left to nonmetallic on the right. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. Boron and carbon are exceptions. They are poor conductors of heat and electricity. Most nonmetallic solids are brittle and are neither malleable nor ductile. The elements become more metallic as we go down a group. The nonmetallic character increases as one goes from left to right across the periodic table. The change from metallic to nonmetallic character is not abrupt as shown by the thick zigzag line in Fig. 3.3. The elements, example, silicon, germanium, arsenic, antimony and tellurium, bordering this line and running diagonally across the periodic table show properties that are characteristic of both metals and nonmetals. These elements are called semimetals or metalloids. 3.7. Periodic trends in properties of elements. There are many observable patterns in the physical and chemical properties of elements as we descend in a group or move across a period in the periodic table. For example, within a period, chemical reactivity tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to a maximum in the group 17 nonmetals. Likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group, whereas within a group of nonmetals, say halogens, reactivity decreases down the group. But why do the properties of elements follow these trends? And how can we explain periodicity? To answer these questions, we must look into the theories of atomic structure and properties of the atom. In this section we shall discuss the periodic trends in certain physical and chemical properties and try to explain them in terms of number of electrons and energy levels. 3.7.1 Trends in physical properties. There are numerous physical properties of elements such as melting and boiling points, heats of fusion and vaporization, energy of atomization, etc. which show periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity. A. Atomic radius. You can very well imagine that finding the size of an atom is a lot more complicated than measuring the radius of a ball. Do you know why? Firstly, because the size of an atom, 1.2 ai, 1.2 times 10 to 10 m in radius, is very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary, the determination of the atomic size cannot be precise. In other words, there is no practical way by which the size of an individual atom can be measured. However, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. One practical approach to estimate the size of an atom of a nonmetallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value, the covalent radius of the element can be calculated. For example, the bond distance in the chlorine molecule, Cl2, is 198 pm and half this distance, 99 pm, is taken as the atomic radius of chlorine. For metals, we define the term metallic radius, which is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 pm, hence the metallic radius of copper is assigned a value of 128 pm. For simplicity, in this book, we use the term atomic radius to refer to both covalent or metallic radius depending on whether the element is a nonmetal or a metal. Atomic radii can be measured by X-ray or other spectroscopic methods. The atomic radii of a few elements are listed in Table 3.6. Two trends are obvious. We can explain these trends in terms of nuclear charge and energy level. The atomic size generally decreases across a period as illustrated in Fig. 3.4a for the elements of the second period. It is because within the period the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. Within a family or vertical column of the periodic table, the atomic radius increases regularly with atomic number as illustrated in Fig. 3.4b. For alkali metals and halogens, as we descend the groups, the principal quantum number, n, increases and the valence electrons are farther from the nucleus. This happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atom increases as reflected in the atomic radii. Note that the atomic radii of noble gases are not considered here. Being monoatomic, their non-bonded radii values are very large. In fact, radii of noble gases should be compared not with the covalent radii but with the van der Waals radii of other elements. B. Ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystals. In general, the ionic radii of elements exhibit the same trend as the atomic radii. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. The size of an anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, the ionic radius of fluoride ion, F, is 136 pm, whereas the atomic radius of fluorine is only 64 pm. On the other hand, the atomic radius of sodium is 186 pm compared to the ionic radius of 95 pm for Na+. When we find some atoms and ions which contain the same number of electrons, we call them isoelectronic species star. For example, O2, F, Na+, and Mg2+ have the same number of electrons, 10. Their radii would be different because of their different nuclear charges. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. C. Ionization enthalpy. A quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom, X, in its ground state. In other words, the first ionization enthalpy for an element X is the enthalpy change, IH, for the reaction depicted in equation 3.1. The ionization enthalpy is expressed in units of kJ mol 1. We can define the second ionization enthalpy as the energy required to remove the second most loosely bound electron. It is the energy required to carry out the reaction shown in equation 3.2. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positively charged ion than from a neutral atom. In the same way, the third ionization enthalpy will be higher than the second, and so on. The term ionization enthalpy, if not qualified, is taken as the first ionization enthalpy. The first ionization enthalpies of elements having atomic numbers up to 60 are plotted in Fig. 3.5. The periodicity of the graph is quite striking. You will find maxima at the noble gases which have closed electron shells and very stable electron configurations. On the other hand, minima occur at the alkali metals and their low ionization enthalpies can be correlated with their high reactivity. In addition, You will notice two trends. The first, ionization enthalpy generally increases as we go across a period and decreases as we descend in a group. These trends are illustrated in Figs 3.6a and 3.6b, respectively, for the elements of the second period and the first group of the periodic table. You will appreciate that the ionization enthalpy and atomic radius are closely related properties. To understand these trends, we have to consider two factors: I, the attraction of electrons towards the nucleus, and 2, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electron from the nucleus by the intervening core electrons. For example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. As a result, the valence electron experiences a net positive charge which is less than the actual charge of +3. In general, shielding is effective when the orbitals in the inner shells are completely filled. This situation occurs in the case of alkali metals, which have single outermost ns electron preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increases across a period. As we go down a group, the outermost electron being increasingly farther from the nucleus, there is an increased shielding of the nuclear charge by the electrons in the inner levels. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy down a group. From Fig 3.6a, you will also notice that the first ionization enthalpy of boron, Z is equal to 5, is slightly less than that of beryllium, Z is equal to 4, even though the former has a greater nuclear charge. When we consider the same principal quantum level, an s electron is attracted to the nucleus more than a p electron. In beryllium, the electron removed during the ionization is an s electron, whereas the electron removed during ionization of boron is a p electron. The penetration of a 2s electron to the nucleus is more than that of a 2p electron, hence the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. Therefore, it is easier to remove the 2p electron from boron compared to the removal of a 2s electron from beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. This arises because in the nitrogen atom, 3 2p electrons reside in different atomic orbitals, Hund's rule, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. Consequently, it is easier to remove the 4th 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. D. Electron gain enthalpy. When an electron is added to a neutral gaseous atom, X, to convert it into a negative ion, the enthalpy change accompanying the process is defined as the electron gain enthalpy, A gauge. Electron gain enthalpy provides a measure of the ease with which an atom adds an electron to form an ion, as represented by equation 3.3. Depending on the element, the process of adding an electron to the atom can be either endothermic or exothermic. For many elements, energy is released when an electron is added to the atom and the electron gain enthalpy is negative. For example, group 17 elements, the halogens, have very high negative electron gain enthalpies because they can attain stable noble gas electronic configurations by picking up an electron. On the other hand, noble gases have large positive electron gain enthalpies because the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. It may be noted that electron gain enthalpies have large negative values toward the upper right of the periodic table preceding the noble gases. The variation in electron gain enthalpies of elements is less systematic than for ionization enthalpies. As a general rule, electron gain enthalpy becomes more negative with increase in the atomic number across a period. The effective nuclear charge increases from left to right across a period, and consequently it will be easier to add an electron to a smaller atom since the added electron on an average would be closer to the positively charged nucleus. We should also expect electron gain enthalpy to become less negative as we go down a group because the size of the atom increases and the added electron would be farther from the nucleus. This is generally the case, Table 3.7. However, electron gain enthalpy of O or F is less negative than that of the succeeding element. This is because when an electron is added to O or F, the added electron goes to the smaller n is equal to 2 quantum level and suffers significant repulsion from the other electrons present in this level. For the n is equal to 3 quantum level, S or Cl, the added electron occupies a larger region of space and the electron-electron repulsion is much less. Electronegativity. A qualitative measure of the ability of an atom in a chemical compound to attract shared electrons to itself is called electronegativity. Unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. However, a number of numerical scales of electronegativity of elements viz. Pauling scale, Mulliken-Jaffe scale, or Redrocho scale have been developed. The one which is the most widely used is the Pauling scale. Linus Pauling, an American scientist, in 1922 assigned arbitrarily a value of 4.0 to fluorine, the element considered to have the greatest ability to attract electrons. Approximate values for the electronegativity of a few elements are given in Table 3.8a. The electronegativity of any given element is not constant, it varies depending on the element to which it is bound. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that you will explore later. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decrease down a group, say from fluorine to astatine, in the periodic table. How can these trends be explained? Can the electronegativity be related to atomic radii, which tend to decrease across each period from left to right, but increase down each group? The attraction between the outer, or valence, electrons and the nucleus increases as the atomic radius decreases in a period. The electronegativity also increases. On the same account, electronegativity values decrease with the increase in atomic radii down a group. The trend is similar to that of ionization enthalpy. Knowing the relationship between electronegativity and atomic radius, can you now visualize the relationship between electronegativity and nonmetallic properties? Nonmetallic elements have strong tendency to gain electrons. Therefore, electronegativity is directly related to that nonmetallic properties of elements. It can be further extended to say that the electronegativity is inversely related to the metallic properties of elements. Thus, the increase in electronegativities across a period is accompanied by an increase in nonmetallic properties or decrease in metallic properties of elements. Similarly, the decrease in electronegativity down a group is accompanied by a decrease in nonmetallic properties or increase in metallic properties of elements. All these periodic trends are summarized in Figure 3.7. 3.7.2 Periodic trends in chemical properties. Most of the trends in chemical properties of elements, such as diagonal relationships, inert pair effect, effects of lanthanoid contraction, etc., will be dealt with along the discussion of each group in later units. In this section we shall study the periodicity of the valence state shown by elements and the anomalous properties of the second period elements, from lithium to fluorine. A. Periodicity of valence or oxidation states. The valence is the most characteristic property of the elements and can be understood in terms of their electronic configurations. The valence of representative elements is usually, though not necessarily, equal to the number of electrons in the outermost orbitals and or equal to 8 minus the number of outermost electrons as shown below. Nowadays the term oxidation state is frequently used for valence. Consider the two oxygen-containing compounds, of2 and Na2O. The order of electronegativity of the three elements involved in these compounds is FO-Na. Each of the atoms of fluorine, with outer electronic configuration to S22p5, shares one electron with oxygen in the of2 molecule. Being highest electronegative element, fluorine is given oxidation state 1. Since there are two fluorine atoms in this molecule, oxygen with outer electronic configuration to S22p4 shares two electrons with fluorine atoms and thereby exhibits oxidation state +2. In Na2O, oxygen being more electronegative accepts two electrons, one from each of the two sodium atoms and thus shows oxidation state 2. On the other hand, sodium with electronic configuration 3s1 loses one electron to oxygen and is given oxidation state +1. Thus, the oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. Some periodic trends observed in the valence of elements, hydrides and oxides, are shown in Table 3.9. Other such periodic trends which occur in the chemical behavior of the elements are discussed elsewhere in this book. There are many elements which exhibit variable valence. This is particularly characteristic of transition elements and actinoids, which we shall study later. B. Anomalous properties of second period elements. The first element of each of the groups 1, lithium, and 2, beryllium, and groups 13 to 17, boron to fluorine, differs in many respects from the other members of their respective group. For example, lithium, unlike other alkali metals, and beryllium, unlike other alkaline earth metals, form compounds with pronounced covalent character. The other members of these groups predominantly form ionic compounds. In fact, the behavior of lithium and beryllium is more similar with the second element of the following group, i.e., magnesium and aluminium, respectively. This sort of similarity is commonly referred to as diagonal relationship in the periodic properties. What are the reasons for the different chemical behavior of the first member of a group of elements in the S and P blocks compared to that of the subsequent members in the same group? The anomalous behavior is attributed to their small size, large charge radius ratio and high electronegativity of the elements. In addition, the first member of group has only 4 valence orbitals, 2s and 2p, available for bonding, whereas the second member of the groups have 9 valence orbitals, 3s, 3p, 3d. As a consequence of this, the maximum covalency of the first member of each group is 4. Example, boron can only form Bf4, whereas the other members of the groups can expand their valence shell to accommodate more than 4 pairs of electrons. Example, aluminium, Al6, 3 forms. Furthermore, the first member of p block elements displays greater ability to form p-pi multiple bonds to itself. Example, C is equal to C, Cc, N is equal to N, Nu, and to other second period elements. Example, C is equal to O, C is equal to N, Cn, N is equal to O, compared to subsequent members of the same group. 3.7.3 Periodic Trends and Chemical Reactivity. We have observed the periodic trends in certain fundamental properties such as atomic and ionic radii, ionization enthalpy, electron gain enthalpy and valence. We know by now that the periodicity is related to electronic configuration. That is, all chemical and physical properties are a manifestation of the electronic configuration of elements. We shall now try to explore relationships between these fundamental properties of elements with their chemical reactivity. The atomic and ionic radii, as we know, generally decrease in a period from left to right. As a consequence, the ionization enthalpies generally increase, with some exceptions as outlined in section 3.7.1a, and electron gain enthalpies become more negative across a period. In other words, the ionization enthalpy of the extreme left element in a period is the least and the electron gain enthalpy of the element on the extreme right is the highest negative, Note, noble gases having completely filled shells have rather positive electron gain enthalpy values. This results into high chemical reactivity at the two extremes and the lowest in the center. Thus, the maximum chemical reactivity at the extreme left among alkali metals is exhibited by the loss of an electron leading to the formation of a cation, and at the extreme right among halogens shown by the gain of an electron forming an anion. This property can be related with the reducing and oxidizing behavior of the elements, which you will learn later. However, here it can be directly related to the metallic and non-metallic character of elements. Thus, the metallic character of an element, which is highest at the extremely left, decreases and the non-metallic character increases while moving from left to right across the period. The chemical reactivity of an element can be best shown by its reactions with oxygen and halogens. Here, we shall consider the reaction of the elements with oxygen only. Elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on extreme left is the most basic, example, Na2O, whereas that formed by the element on extreme right is the most acidic, example, Cl2O7. Oxides of elements in the center are amphoteric, example, Al2O3, As2O3, or neutral, example, Co, No, N2O. Amphoteric oxides behave as acidic with bases and as basic with acids, whereas neutral oxides have no acidic or basic properties. Among transition metals, 3D series, the change in atomic radii is much smaller as compared to those of representative elements across the period. The change in atomic radii is still smaller among inner transition metals, 4F series. The ionization enthalpies are intermediate between those of S and P blocks. As a consequence, they are less electropositive than group 1 and 2 metals. In a group, the increase in atomic and ionic radii with increase in atomic number generally results in a gradual decrease in ionization enthalpies and a regular decrease, with exception in some third period elements as shown in section 3.7.1d, in electron gain enthalpies in the case of main group elements. Thus, the metallic character increases down the group and non-metallic character decreases. This trend can be related with their reducing and oxidizing property, which you will learn later. In the case of transition elements, however, a reverse trend is observed. This can be explained in terms of atomic size and ionization enthalpy. Summary. In this unit, you have studied the development of the periodic law and the periodic table. Mendeleev's periodic table was based on atomic masses. Modern periodic table arranges the elements in the order of their atomic numbers in 7 horizontal rows, periods, and 18 vertical columns, groups or families. Atomic numbers in a period are consecutive, whereas in a group they increase in a pattern. Elements of the same group have similar valence shell electronic configuration and therefore exhibit similar chemical properties. However, the elements of the same period have incrementally increasing number of electrons from left to right and, therefore, have different valencies. 4 types of elements can be recognized in the periodic table on the basis of their electronic configurations. These are S block, P block, D block and F block elements. Hydrogen with 1 electron in the 1s orbital occupies a unique position in the periodic table. Metals comprise more than 78% of the known elements. Nonmetals, which are located at the top of the periodic table, are less than 20 in number. Elements which lie at the border line between metals and nonmetals, example, C, Ge, as, are called metalloids or semimetals. Metallic character increases with increasing atomic number in a group, whereas decreases from left to right in a period. The physical and chemical properties of elements vary periodically with their atomic numbers. Periodic trends are observed in atomic sizes, ionization enthalpies, electron gain enthalpies, electronegativity and valence. The atomic radii decrease while going from left to right in a period and increase with atomic number in a group. Ionization enthalpies generally increase across a period and decrease down a group. Electronegativity also shows a similar trend. Electron gain enthalpies, in general, become more negative across a period and less negative down a group. There is some periodicity in valence. For example, among representative elements, the valence is either equal to the number of electrons in the outermost orbitals or 8 minus this number. Chemical reactivity is highest at the two extremes of a period and is lowest in the center. The reactivity on the left extreme of a period is because of the ease of electron loss or low ionization enthalpy. Highly reactive elements do not occur in nature in free state, they usually occur in the combined form. Oxides formed of the elements on the left are basic and of the elements on the right are acidic in nature. Oxides of elements in the center are amphoteric or neutral. Thank you for tuning in. Give this video a thumbs up if it was helpful and subscribe for the upcoming videos. Check out more videos from the playlist. Also comment down if you have some queries or suggestion.
Came out of the smoke, you can't see me, I hope. A trump card, ace of spades, time for you to fold. I'm taking what is yours, make sure you go broke. So you can go back, listen to the bullshit that you spoke, and come back to realize the fact that this was not a joke. Another sucker teaching other brothers to be woke. This motherfucker grew up watching Indian TV soaps. Another chuckle, I'ma shove the mic in your throat.